Welcome to this explainer. Today, we're going to be exploring the hidden mechanics behind our modern world. We're taking something that honestly feels a bit like pure magic, magnetism, and unpacking the brilliant, highly structured engineering that makes it tick. So let's just dive right in. Think about this for a second. What do a massive crane in a wrecking yard, a life-saving hospital MRI machine, and a highly theoretical deep space probe actually have in common? On the surface, they are wildly different technologies. But under the hood, they all rely on the exact same invisible force, a force we've figured out how to harness, scale, and deeply control. I'm talking about the electromagnet. Here's a quick look at our agenda for today's journey. First, on-demand magnetism. Second, a spark of history. Third, anatomy of an electromagnet. Then we'll cover from doorbells to MRIs. And finally, deep space and beyond. Starting off with Section 1, on-demand magnetism, the superpower of control. So when we look at the difference between permanent magnets, the ones currently holding up photos on your fridge, and electromagnets, a really clear distinction emerges. Drawing from Baiju's educational resources, we see that a permanent magnet's field is basically always on. It's totally fixed. But an electromagnet, its magnetic properties exist only when an electric current is actually flowing through it. That means the strength is totally adjustable, and you can even flip the poles just by reversing that current. It essentially gives us temporary, on-demand magnetism. It is the absolute superpower of control. You can turn the magnetic force on to pick up an entire car, and then literally just switch it off to drop it. You simply cannot do that with a permanent magnet. Moving to Section 2, a spark of history, from accidental discovery to heavy lifting. Now, this technology didn't just appear overnight. It was iterated on over time. Looking at STM Magnetics records, the whole thing actually kicked off back in 1820. That's when Danish scientist Hans Christian Ørsted accidentally, yes, completely by accident, noticed a compass needle reacting to a battery being switched on and off in his lab. He realized right then that electric currents create magnetic fields. Fast forward just 4 years later, and William Sturgeon invents the first practical electromagnet. Because he wrapped bare copper wire around varnished iron, he could really only use a single spread-out layer of wire. Because of that, his magnet only weighed about 7 ounces and could lift 9 pounds. Pretty impressive for the time, but definitely limited. Then came the giant leap. In 1830, American scientist Joseph Henry used wire insulated with silk. Because it had that insulation, he could tightly wrap thousands of turns of wire in multiple layers without them shorting out. His magnet? It lifted over 2,000 pounds. Insulation was absolutely the key to scaling up this invisible force. That brings us to Section 3, Anatomy of an Electromagnet, building your own magnetic field. According to Instructables and How Stuff Works, the actual mechanical structure here is surprisingly simple. You literally just take an iron core. Something like a standard 6-inch nail works perfectly. Tightly wrap some 20 or 22 gauge insulated copper wire right around it. Then just strip the ends of the wire and connect them to the positive and negative terminals of a battery, like your standard D cell. The second you close that circuit, electricity flows and boom, you have instantly created a working electromagnet right there on your desk. But what is actually happening inside that nail? Well, that wrapped core is known as a solenoid, and the physics behind it is just fascinating. See, before you connect the battery, the atoms inside that iron nail are arranged completely at random. They're pointing in all sorts of different directions. But the moment that electric current flows through your copper coil, it creates a magnetic field that physically penetrates the iron core. This field essentially forces those random atoms, specifically these small regions called domains, to snap right into alignment. With all of those atomic domains suddenly facing the exact same direction, the magnetic field just grows exponentially. You are literally reorganizing the atomic structure of the iron to generate physical force. How cool is that? But as engineer Leslie Green points out, optimizing this coil isn't quite as straightforward as you might think. You might be sitting there thinking, hey, I'll just add hundreds of really thick layers of wire to make it incredibly strong. But actually, wire diameter and tightness really matter here. As a turn of wire gets further away from the center axis, its circumference naturally increases. That means an outer turn of wire has double the electrical resistance of an inner turn, and higher resistance means more power is just lost as heat. At the very same time, because it's further away, that outer turn has only half the magnetic influence on the core itself. So ironically, a massively thick coil actually becomes remarkably inefficient. And this leads us to an absolutely crucial engineering concept, the duty cycle. Think about it like this. Imagine you have an electromagnet that's rated for 5 pounds of continuous pull, but you temporarily need it to pull 9 pounds. You can actually double the voltage to get that extra force, but doing so quadruples the power, which creates a massive amount of heat. If you just leave it turned on, the insulation will literally melt and the magnet will burn out entirely. But if you apply that overload power for just a tiny fraction of a second, say a 10% duty cycle, it survives. It's exactly like sprinting versus walking. You can sprint incredibly fast, but only for a really short burst before you need to stop and rest. By carefully managing the duty cycle, engineers can extract massive amounts of force from surprisingly small electromagnets without causing a catastrophic failure. Let's move to section 4, from doorbells to MRIs scaling up the invisible force. The sheer versatility of the electromagnet is just incredible when you really look at it. Take a traditional doorbell. Pushing the button closes a circuit, which creates a temporary magnetic pull that physically smacks a metal clapper against a bell. Super simple, right? Now look at a computer's hard drive. Tiny electromagnetic currents magnetize microscopic pieces of metal on a disk, physically aligning them to store your digital ones and zeros. Moving up to the absolute extremes, particle accelerators use massive electromagnets to actually bend and control the trajectory of subatomic beams traveling near the speed of light. And in high-tech research labs, pulsed field magnets use that exact sprinting duty cycle concept we just talked about. They fire off incredibly brief bursts of current to generate unfathomably massive magnetic fields. We're talking between 50 and 100 Tesla for just tens of milliseconds at a time. It's the exact same fundamental physics as our simple 6-inch nail, just scaled all the way up to the absolute limits of human engineering. And speaking of pushing limits, let's consider the hospital MRI machine. According to the eMRI medical source, there are two main types of MRI electromagnets. First, you have resistive magnets. These are basically massive versions of what we've been discussing, giant coils of wire that require huge amounts of continuous power and dedicated water cooling systems. But superconducting magnets, that is where things get really wild. These coils are actually cooled with liquid helium to near absolute zero, and at that ridiculously cold temperature, the wire achieves zero electrical resistance. That allows for incredibly powerful, perfectly stable magnetic fields with absolutely no power loss. But the stakes are incredibly high here. If that cooling system fails, an event technically called a quench, the sudden return of electrical resistance creates massive instant heat. That heat violently boils off the liquid helium into a huge, rapidly expanding cloud of gas that has to be safely vented right out of the building. It is quite literally high-stakes physics, saving human lives every single day. Finally, Section 5. Deep space and beyond, jolting our way to the stars. So currently, space travel relies entirely on chemical propellant. You know the drill. You burn fuel to push yourself forward. But David Goodwin, a program manager at the U.S. Department of Energy, has proposed a totally propellantless spacecraft. It would use a solenoid made of super-cooled niobium tin wire. With a highly specialized solid-state switch, you'd pulse electricity into the magnet about 400,000 times a second. Because for the first few nanoseconds of being powered on, a supercooled electromagnet actually vibrates. Goodwin proposes placing an isolated metal plate nearby to intentionally create an asymmetric magnetic field. The idea is, if you can harness that extremely high-frequency vibration in one specific direction, it could provide a continuous forward jolt. Powered by just a small onboard nuclear reactor, this kind of electromagnetic propulsion could theoretically jolt a craft all the way to the heliopause, the very edge of our solar system, at a fraction of the speed of light. No rocket fuel required. Now, of course, scientists are naturally skeptical about this, and it absolutely requires technology pushed to its absolute breaking point. But I just love this quote from Goodwin himself. He said, "It is highly speculative, and on my most wildly optimistic days, I think there's 1 chance in 10 that it might work." I think that brilliantly captures the reality of bleeding-edge science. Yes, it's highly speculative, but remember, a century ago, the mere idea of leaving the Earth's atmosphere was considered total science fiction. The sheer potential of harnessing electromagnetic vibration to literally sail to the stars is just breathtaking to think about. So, as we wrap up this explainer today, I want to leave you with a thought. Take a look around the room you're sitting in right now. Where are the hidden magnetic forces quietly shaping your world? From the microscopic data stored on the device you're watching this on, to the motors humming in your home appliances, all the way to grand visions of deep space probes. The power to align the very atoms of the universe on demand is literally everywhere. It's this incredible invisible force, tamed and controlled by human ingenuity, and it quite literally holds our modern world together. Thank you so much for joining me on this deep dive. Stay curious and keep looking for the hidden engineering all around you.